Hey class, so I wanted to explain some of the curve sketching and give you some more examples of it. It just felt like it wasn't as reviewy as I thought it might be. So I'm going to pick some questions that I just pulled off of online and kind of work through them. I would recommend that you pause and try to see how much you can get through before you kind of run into a little bit of a brick wall, and then kind of play the video again and see where we get to. So here's the function that we're going to work with, this x cubed minus 9x divided by 3x squared minus 6x minus 9. All right, so the first thing we want to do is factor this thing. So my bad, I was just trying to turn something off my computer. So the first thing we want to do is try to factor. So in the numerator, I can pull out an x, and we're going to left with x squared minus 9, and then I can take that one more step because I can factor that x squared minus 9 into x minus 3, x plus 3. In the denominator, I have a greatest common factor of 3 that I could pull out. So I can get a 3 and then an x squared minus, 2x, let me just erase that, minus 2x minus 3. And that can factor as well, right? So I have a 3 left over, but this x squared minus 2x minus 3 is x minus 3, x plus 1. All right, so we have that. So now we have this. Before we write this simplified version here, let's find the domain, right? So we're going to have all real numbers except for where the denominator is equal to 0. So the denominator is going to equal 0 when x minus 3 is equal to 0, or when x is equal to 3. Alternatively, when x plus 1 is equal to 0, we're also going to get a place where our function doesn't exist. So we have this x plus 1 is equal to 0, so x is equal to negative 1. Right, so our domain is going to be all real numbers except for 3 and negative 1. Right, alternatively, if you want to write this in interval notation, it's negative infinity to negative 1, and then the union of negative 1 to 3, and both of those are parentheses, not brackets. All right, so then we can do some cancellation. This x minus 3 and that x minus 3 cancel, which means we're going to get a whole at that canceled root. So we're going to get a whole when x is equal to 3. Our simplified version is x times x plus 3, and we have a 3 in the bottom and an x plus 1. Alright, so I like to figure out the whole at this point because I think it's the easiest thing to forget. So to figure out what the whole is, we're just going to plug in 3 into our simplified version. Alright, so we're going to plug 3 in. Let me just turn this to an x for a second. X plus 3, and 3 x plus 1. Alright, so when we plug in 3, we're going to end up with f of 3 equals 3 plus 3 over 3 plus 1. Alright, so you can be fancy, we can cancel these 3's out if we want, or you could just kind of like get your number. We're going to get 3 times 6 over 3 times 4, so that's 18 over 12, which turns into 3 halves. So this is the y coordinate of our whole. So we have a whole at 3 and then 3 halves, or 1 1/2. Alright, so that part's done. So the next thing is let's find our vertical asymptote. A vertical asymptote is going to occur when the denominator is equal to 0 now. It's also the only other thing that's not in our domain. Right, so 3 was the whole, right? So that's the whole. So this negative 1 is going to be the vertical asymptote. Where if you set 3 times x plus 1 equal to 0, you're going to get x equals negative 1. Right? So that's going to be our vertical asymptote. So we can start to fill in some pieces here. Right? So if this is 1, negative 1 I should say, if this is negative 1, we're going to have a vertical asymptote here. So that's the line x is equal to negative 1. We're also going to have a whole. We can kind of plug that whole in at this point. Right, so it's going to be 3 over 2. So this is maybe 1 and 2. We're going to get a hole somewhere over here-ish. All right, so then let's see what else we could do. So we can figure out the x-intercepts now. So if I look at our simplified function, right, we're setting y equal to 0 to find the x-intercepts. So it's x times x plus 3 over this 3x plus 1. But the only thing we really care about is when this numerator is equal to 0. Because 0 over whatever, as long as that whatever isn't 0, is going to equal 0. So what we're really looking for is when is x times x plus 3 equal to 0? Well, we're going to use what's called the zero product principle that you might remember from Algebra 2. We're going to say this could equal 0, or the x plus 3 could equal 0, which means that, well, here x is equal to 0, and here x is equal to negative 3. Right, so that's going to be our two x intercepts, 0 and negative 3. So we have an x-intercept there, and we have an x-intercept over here at negative 3. Okay, we're doing it. We're getting there. So we're going to have negative 3, 0, and 0, 0. Now, if 0, 0 is an x-intercept, it also means that the y-intercept is 0, 0. And the reason is, well, if you pass through the origin, 0, 0, y is equal to 0 at that point. If we were just finding the y-intercept normally, let me erase some of this stuff. If we're just finding the y-intercept normally, then what we would do is we would plug in 0 for x and see what we end up with. Right? So let me pretend that we don't know what our x-intercept is at, our y-intercept is at this point. So if we in our function, right, so our simplified function, if we plug in 0, we're going to get 0 times 0 plus 3, 3, 0 plus 1. So we're going to get 0 times 3 over 3 times 1. We're going to get 0 over 3, or 0. So that means that our y-intercept is 0, like we knew. All right, so then now, second to last thing, let's find our horizontal asymptote. So to find the horizontal asymptote, it doesn't matter which function you look at, the original function or the simplified function. We're just looking for the ratio of the degrees. So initially we had a degree of 3 and a degree of 2. So the degree of the top was bigger than the degree of the bottom. This was that first case that we had in class. If we looked at the simplified function, this is degree 2. This is degree 1. So again, the degree of the top is bigger than the degree of the bottom. It won't matter which one you look at. They're both going to give you the same answer. So what that means, if the degree of the top is bigger than the degree of the bottom, there's no horizontal asymptote in this question. So we don't even have to worry about graphing that. And then finally, the last thing that we need to do is figure out what is our function going to do. So to that end, we need to set up a table of signs. So in the table of signs, remember, we graph x-intercepts. So we had an x-intercept of negative 3. We graph vertical asymptotes. So negative 1, or we plot them, I should say. And we have another 0 at 0. All we care about is the sign. We don't care about what the actual value is. All we care about is the sign. All right, so let's pick some values. Use the simplified function. So we have x times x plus 3 over 3x plus 1. Now, nice things that we can do here. We don't care about this 3. This 3 is always positive. It doesn't really tell us anything about the signs. So if I pick something that's less than negative 3, suppose I say x is equal to negative 4, let's see what we end up with. We're going to get a negative. I don't even care about the 4. I'm going to get a negative. Negative 4 plus 3 is a negative. negative 4 plus 1 is also a negative. So I get 3 negatives. So on the domain negative infinity to negative 3, the function is going to be negative. If we pick some value between negative 3 and negative 1, suppose we say x is equal to negative 2. So when I plug in, I'm going to get negative 2 plus 3 is positive, and negative 2 plus 1 is negative. So on this interval, it's going to be positive. If I pick some value between 0 and negative 1, so suppose I pick a negative 1/2, so I'm going to get a negative 1/2 plus 3 is positive, and negative 1/2 plus 1 is also positive. So we only have one negative here, so it's going to be negative on that part of the domain. And then when I pick anything bigger than 0, we actually know, right? If you were to plug in 3, right, we got a positive number, but just pick some other value if you don't remember that you've already figured out what it is based on this hole. So if we pick, say, x is, I don't know, 2, we're going to get a positive. X plus, or 2 plus 3 is also positive, and 2 plus 1 is also positive, so we get a bunch of positives. So we know what this function is going to do on these intervals. All right, so we have no horizontal asymptote, so I don't really care if you get the exact thing going on here, but we have some function, it's negative, it has to come up and hit this 0. All right, so we've kind of graphed this part of the domain so far. From negative 3 to negative 1, it's going to be positive, so it's going to shoot off towards this asymptote. So we've graphed that part. From negative 1 to 0, it's going to be negative, so it has to come up and hit this 0. And then from 0 to infinity, it's going to be positive. It has to go through this hole and do something so that it's off like that. Right, so this is a good enough general sketch of the rational function. So I'll do a couple more of these, not in this much depth, just so you can kind of see the basics again of what's going on here. All right, so should be an arrow there. All right, so good luck.